Have you ever wondered what it would be like to control a computer or a robot with your mind? Imagine being able to type without using your hands, play video games without a controller, or even move a prosthetic limb with your thoughts. Sounds like science fiction, right? Well, not anymore. Thanks to a technology called brain-computer interfaces, or BCIs for short, this is becoming a reality. In this video, we will explore what BCIs are, how they work, what they can do, and what challenges they face. We will also look at some of the most exciting and cutting-edge examples of BCIs in action. So buckle up and get ready for a mind-blowing journey into the world of brain-computer interfaces. So, what exactly are brain-computer interfaces? A BCI is a direct communication pathway between the brain and an external device, most commonly a computer or a robotic limb. BCIs can measure brain activity, extract features from that activity, and convert those features into outputs that replace, restore, enhance, supplement, or improve human functions. BCIs can also provide feedback signals to the brain for neuromodulation. But how do BCIs measure brain activity? Well, there are different ways of doing that, depending on how close the electrodes get to the brain tissue. There are three main types of BCIs: non-invasive, partially invasive, and invasive. Non-invasive BCIs use electrodes that are attached to the scalp or worn as a cap. They record electrical signals from the brain through the skin and the skull. The most common technique for non-invasive BCIs is electroencephalography, or EEG for short. EEG measures the voltage fluctuations resulting from the synchronized activity of thousands of neurons in the brain. EEG has the advantage of being cheap, portable, and easy to use. However, it also has some drawbacks, such as low spatial resolution, poor signal quality, and susceptibility to noise and artifacts. Partially invasive BCIs use electrodes that are implanted under the skull but above the brain tissue. They record electrical signals from the surface of the cortex, which is the outer layer of the brain. The most common technique for partially invasive BCIs is electrocorticography, or ECOG for short. ECOG measures the voltage fluctuations resulting from the activity of groups of neurons in the cortex. ECOG has the advantage of having higher spatial resolution, better signal quality, and less noise and artifacts than EEG. However, it also has some drawbacks, such as requiring surgery, causing inflammation and scarring of the tissue over time, and being limited to recording from the cortex only. Invasive BCIs use electrodes that are implanted directly into the brain tissue. They record electrical signals from individual neurons or small clusters of neurons in different regions of the brain. The most common technique for invasive BCIs is microelectrode array, or MAIA for short. MAIA measures the voltage fluctuations resulting from the activity of single neurons or small clusters of neurons in different regions of the brain. MAIA has the advantage of having the highest spatial resolution, the best signal quality, and the ability to record from deep brain structures. However, it also has some drawbacks, such as requiring invasive surgery, causing tissue damage and immune response, and being prone to biofouling and signal degradation over time. So, as you can see, there is a trade-off between invasiveness and performance when it comes to BCIs. The choice of BCI type depends on the application and the user's preference. For example, non-invasive BCIs are more suitable for healthy users who want to use BCIs for entertainment or enhancement purposes, while invasive BCIs are more suitable for patients who need BCIs for restoring lost functions or treating disorders. But how do BCIs convert brain signals into outputs? Well, that's where the magic of machine learning comes in. Machine learning is a branch of artificial intelligence that enables computers to learn from data and make predictions or decisions. Machine learning algorithms can be trained to recognize patterns in brain signals and associate them with specific commands or intentions. For example, a machine learning algorithm can learn to decode what letter a user wants to type by analyzing their brain signals when they look at a flashing keyboard on a screen. Or, a machine learning algorithm can learn to control a robotic arm by analyzing the brain signals of a user when they imagine moving their own arm. Machine learning algorithms can also provide feedback signals to the brain for neuromodulation. Neuromodulation is the process of altering the activity of neurons or neural circuits by applying electrical or chemical stimuli. Neuromodulation can be used to enhance or suppress certain brain functions, such as memory, attention, mood, or pain. For example, a machine learning algorithm can learn to stimulate specific regions of the brain that are involved in learning and memory when a user performs a cognitive task. Or, a machine learning algorithm can learn to inhibit specific regions of the brain that are involved in depression or chronic pain when a user reports their mood or pain level. Machine learning algorithms are constantly improving and becoming more powerful and adaptable. They can also learn from multiple sources of data, such as EEG, ECOG, MEA, eye tracking, facial expression, etc., and combine them to create more robust and accurate BCIs. So, what can BCIs do? Well, the possibilities are endless. BCIs can enable users to interact with computers and machines in novel and intuitive ways. BCIs can also help users to improve their cognitive and physical abilities, or restore them if they are impaired by injury or disease. Here are some of the most amazing and inspiring examples of BCIs in action. Here are some of the most amazing and inspiring examples of BCIs in action. Communication. BCIs can enable people who are unable to speak or move due to conditions such as locked-in syndrome, amyotrophic lateral sclerosis, or stroke to communicate with others using their brain signals. For example, a BCI can allow a user to type words on a screen by selecting letters from a flashing keyboard with their eyes or thoughts. Or, a BCI can allow a user to speak by synthesizing speech from their brain signals that encode speech intentions. Gaming. BCIs can enhance the gaming experience by adding a new dimension of interaction and immersion. For example, a BCI can allow a user to control a character or an object in a game with their thoughts or emotions. Or, a BCI can adapt the game difficulty or content based on the user's cognitive state or preferences. Neuroprosthetics. BCIs can restore or augment the motor functions of people who have lost or impaired limbs due to injury or disease. For example, a BCI can allow a user to control a robotic arm or leg with their thoughts by mimicking the natural movements of their own limbs. Or, a BCI can provide sensory feedback to the user by stimulating their brain with artificial sensations such as touch or pain. Bioelectronic medicine. BCIs can treat or prevent various neurological disorders and conditions by modulating the activity of specific brain regions or circuits. For example, a BCI can stimulate the brain regions that are involved in depression or chronic pain to alleviate the symptoms or induce positive emotions. Or, a BCI can inhibit the brain regions that are involved in epilepsy or Parkinson's disease to prevent or reduce seizures or tremors. Brain and machine intelligence integration. BCIs can enhance or augment the cognitive abilities of healthy users by interfacing their brains with artificial intelligence systems. For example, a BCI can allow a user to access information from the internet or a cloud database directly with their thoughts. Or, a BCI can allow a user to learn new skills or languages faster by transferring knowledge from an AI system to their brain. As you can see, BCIs are an amazing and powerful technology that can revolutionize many aspects of our lives. However, BCIs also pose some ethical and social challenges that need to be addressed. For example, how do we ensure the privacy and security of our brain data? How do we regulate the use and access of BCIs? How do we balance the benefits and risks of BCIs? How do we respect the autonomy and dignity of BCI users? How do we deal with the potential changes in our identity and sense of self that BCIs might cause? These are some of the questions that we need to think about as we enter the era of brain-computer interfaces. We hope you enjoyed this video and learned something new about BCIs. If you did, please give us a thumbs up and subscribe to our channel for more videos like this. And don't forget to leave your comments and questions below. We would love to hear from you. Thank you for watching and see you next time.